Numbers are a critical part of the way we understand our world and have enabled us to think in many different ways. In this video series, I would like to explore numbers, but not just any ordinary numbers. We are going to explore big numbers. Last time, we used up arrow notation to describe the massively large Moser's number. We started with this huge quadruple arrow structure, which is used to describe the number of arrows in this number, which in turn describes the number of arrows in this number, which is Moser's number. Extraordinarily huge. In 1977, a number far beyond even Moser's number showed up in a Scientific American and became so widely known it even appeared in the Guinness Book of World Records 3 years later. This number was described by Ronald Graham, a mathematician who used this number in a mathematical proof, and at the time was the largest number ever to be used in such a proof. This is none other than Graham's number, which is written as G64. Let's see how this number is defined. We once again start with 3 quadruple arrow 3. This describes the amount of arrows for the next number, which describes the amount of arrows in the next number. But now we continue on, with each level describing the amount of arrows in the next level, continued for 64 levels. This results in a number that is insanely large and is impossible to write out completely, even in Knuth up arrow notation. But let's take a look at that massiveness from another perspective. Let's count the number of digits that Graham's number has and call that value n1. Now this number is also going to be mind-numbingly large. So let's count the number of digits in n1 as well, calling that value n2. This is also ridiculously large. So we will count the digits in this number too, calling that value n3. We can repeat this process many times, finding the number of digits in n3 and in n4 and n5 and so forth, as we try to find a number that we can actually manage. So how far up the chain do we have to travel? Well, it turns out that we have to repeat the process a lot in order to get a number with less than a Google digits. This process, in fact, takes so many repetitions that to make it easier, let's give the number of repetitions a value, z. How big is z, the number of repetitions? Turns out it's really, really big. But we can use the same process here, where we find the number of digits and call that z1, and then find the number of digits in z1 and call that z2, and so on and so forth. But wait, how many times do we have to repeat this process with z to get a number of digits smaller than Google? Well, we do it so much that we can name the new number. Let's call it y. And as you might have guessed, y is huge. So we can repeat this pattern, running our process on y so much that we need a new value, x, and repeating the process with x until we need a new value, w. And we can continue till we use up the whole alphabet and even start over. So we run through the alphabet again and again. In fact, we have to repeat this process so much that even the number of times we have to go through the alphabet is still much larger than Google, meaning we couldn't ever write this number in our universe. And remember, this is all just to describe the number of digits of Graham's number. So Graham's number has often become synonymous with the concept of a truly massive number. In fact, we have reached a point where perhaps even Knuth's up arrow notation is getting a tad cumbersome. So perhaps we need another tool to track these massively growing numbers. And we'll talk about this new tool in the next video. The world of big numbers goes as far as you are willing to go. So please join me for the next video where we explore big numbers.